Okay, so welcome to the transshipment problem. So please watch the previous video that has the transportation problem in it. Understanding the transportation problem will give you a leg up with the transshipment problem, and I will assume that you know what we already talked about with the transportation problem for the transshipment problem. So the transshipment problem is an extension of the transportation problem. It is used in scenarios where we know the supply, just like the transportation problem. We know where our supply locations are. We know what our demand locations are. But supply doesn't travel directly from the supply locations to the demand location. So goods go from the supply locations to intermediate or transshipment locations, and then from transshipment locations they are transported to the demand locations. We can think of manufacturing plants, distribution centers, and say retail locations. It's something along those lines. So it's a much longer supply chain than just directly from supply locations to demand locations. Now the objective here is again to find which supply locations serve which transshipment locations, and which transshipment locations supply which demand locations, and how you can do all of this at minimum cost. Now we assume that we know everything about the supply locations and the demand locations, and we also know where the intermediate locations, the transshipment locations are. So we know the cost of transporting from supply location to transshipment locations, and the cost of transporting from the transshipment locations to the demand locations. So we know all of these costs. So this is what the network representation looks like. So you have supply locations 1 and 2, intermediate or transshipment locations 3, 4, and 5, and demand locations 6 and 7. So you have C13, which is the cost of transporting from supply location 1 to transshipment location 3, and you have C36 is the cost of transporting from transshipment location 3 to demand location 6. That's how this network is represented. So the once you represent this as a network, the way you set up the problem is pretty similar to the way you set up the transportation problem. The only difference being that items don't go directly from the supply location to the demand location. We just try to make sure that they go through the transshipment location, so the intermediate nodes. Now, one of the assumptions that we are going to make, and this is an important assumption, is that all the supply that comes into the transshipment locations from all supply locations, everything that comes into the transshipment locations is supplied out to some demand locations. We'll assume that inventory doesn't accumulate at the intermediate nodes. Now it might temporarily accumulate, but it doesn't accumulate over a period of time. So anything that comes in is shipped out. So that's an assumption that is made. Right? So with that in mind, so the problem, the objective function, the problem look like this. So again, we'll assume the total supply is more than total demand. So like in the previous scenario with the transportation model, if the total supply is less than total demand, all we have to do is we have to switch the equal to and the less than or equal to side. So if the total supply is less than total demand, this will be an equal to constraint, and this will be a greater than or equal to constraint. So the cost function, now we have two components. This is the cost of transporting everything from supply locations to the intermediate locations, and from to the transshipment locations. This is the cost of transporting from the transshipment locations to the demand locations. Oh, there is a tiny error here. Let me quickly fix that. So this is the cost of the first step of the supply chain. This is the cost of the second step of the supply chain. And again, this constraint is familiar. It should be familiar to you with from the transportation problem. All the supply that goes out of a particular supply location cannot exceed the capacity of that supply location. And the demand constraint, all the supply that comes into a particular demand location from all the transshipment locations has to equal the demand at the demand location, And finally, like I said, the transshipment constraint, which is the total supply that comes into a particular transshipment location, is equal to the total supply that goes out of the transshipment location. So you notice that this summation is over all the supply locations and this summation is over all the demand locations. What does that mean? So what it essentially means is that, for example, if we take number 3, all the supply that comes in, so x13 plus x23, everything coming into node 3, the transshipment location 3, should be equal to x36 plus x37, everything going from the transshipment location to the demand location 6 and from the transshipment location 3 to demand location 7. So again, x13 plus x23 will be equal to x36 plus x37. Similarly, x14 plus x24 will be equal to x46 plus x47, and so on. So the decision variables, when you come up with the decision variables, everything coming in to the particular transshipment location should be equal to everything going out of the transshipment location. So those are the transshipment constraints, and those are the extra constraints that you have for the transshipment problem. So with that in mind, so here is an example. So north side and south side facilities of Xeron Industries supply 3 firms. So these are the 2 facilities, and they supply Xerox, Hughes, and Rockright with customized shelvings for their offices. They both also, the north side and south side locations, order shelving from 2 manufacturers, Arnold Inc. and Supershelf. Arnold manufactures and Supershelf Inc. And both of these facilities, Arnold and Supershelf, have a capacity of 75. All the numbers given here are the cost of transporting from Arnold to Xeron North, Arnold to Xeron South, Supershelf to Xeron North, and Supershelf to Xeron South, and so on. So these are the costs of installing the shelving at the various locations, and also transportation and installing. So I should say transportation and installation, not just installation. And these are all the cost values that are given. And you also know that the supply at Arnold and Supershelf, so capacity is 75 units each, and the demand at Xerox, Hughes, and Rockright is 50, 60, and 40. So 50 here, 60 here, and 40 here. One thing you'll notice is that here the total demand is 50 plus 60 plus 40, that's 150. The total supply is 75 plus 75, which is 150 also. Total supply is equal to total demand, and this is called a balanced supply chain. It's very, very rare that you come across a balanced supply chain, but this is an example of a balanced supply chain. So let's see how we can, when you have a problem like this, which is a transshipment problem, how do you formulate the problem in Excel and how do you solve it? So we know what the formulation looks like, the mathematical formulation. So you're going to take this mathematical formulation and formulate the problem in Excel and then solve it, just like we did the transportation problem. So let's look at the Excel solution. All right. So again, all right. So decision variables. So we have 2 sets of decision variables here. One set of decision variables are the amounts that get transported from the 2 suppliers to the Xeron North and Xeron South, and of course the amounts that are transported from Xeron North, Xeron South to the 3 office locations. So we have 2 sets of decision variables, and we are going to look at both sets. Just like last time. Just going to get rid of these numbers. Alright, so just like last time, I'm just going to color code them. So I know that these are my decision variables right here. two sets of decision variables. So these set of decision variables tell me how many units get transported from in the first stage of the supply chain, and these decision variables tell me how many units get transported from which location to which location in the second part of the supply chain. All right. So now that we have set up the decision variables, the next step is to set up the objective function. So the objective function is to minimize total cost of both stages of the supply chain. So how do we calculate this total cost? So it's simple. It's similar to what we did last time. So $5 is the cost of transporting from Arnold to Xeron. So it's $5 times the number of units, $8 times the number of units, $7 times the number of units that Supershelf supplies to Xeron, $4 times the number of units that Supershelf supply to Xerox. So again, we're multiplying corresponding numbers and adding them together. This will be the cost of the first part of the supply chain. The cost of the second part of the supply chain, which is transportation and installation at the demand locations, will be $1 times the number, $5 times this number, $8 times this number, $3 times this number, $4 times this number, and $4 times this number. So again, we're going to multiply the corresponding values together. So what we can do is we can write the total cost for the two stages as two separate sum product functions, and we can add them up. So say sum product. So sum product of the costs of transporting from the manufacturers to Xeron North and Xeron South times the corresponding decision variables. So we have multiply with the corresponding values and then add them up, sum of products, plus, so this is the cost of the first part of the supply chain plus cost of the second part of the supply chain. So sum product of the corresponding cost values and the variable values. So two sum product functions for the two stages of the supply chain, and that's the total cost, and we want to minimize this total cost. There you go. Now once we have this, we are going to write three sets. So we have decision variables and the objective function. Now we're going to write three sets of constraints. We will have supply constraints, demand constraints, and transshipment constraints. Let's write the supply constraints first. Supply constraints, so there are two supply locations, Arnold and Supershelf. So supply and constraint. This is the capacity. Capacity is 75 and 75. And the total supplied from Arnold to Xeron North and Xeron South is the total supply. Everything coming out of Arnold going to Xeron North plus everything coming out of Arnold going to Xeron South. Similarly, everything going from Supershelf to Xeron North plus everything going from Supershelf to Xeron South. Then we have the demand constraints. Just like last time, I'm going to write demand constraints as columns. So this will be supplied demand. We know what the demand values are at Xerox, Hughes and Rock, right? So it's 50, 60 and 40. So you know exactly what the demand values are. And so total amount supplied to Xerox is everything coming out of Xeron North to Xerox plus everything coming out of Xeron South to Xerox. So everything coming out of the intermediate locations, the transshipment locations, which is essentially the companies going to Xerox. So everything supplied to Xerox should be equal to 50 units. That's the demand at Xerox. Again, I can copy the formula out and say everything coming into Hughes has to be 60. Sum of everything coming into Rockwright has to be 40. So those are the demand constraints. And finally, we are going to write transshipment constraints. So these are slightly more involved. Just slightly more. So the two transshipment locations are Xeron North and Xeron South. Coming in and going out. Right? So everything coming into Xeron North is the sum of everything coming in to Xeron North from both Arnold and Supershelf. So Arnold to Xeron North, Supershelf to Xeron North. Everything coming into Xeron North should be equal to everything going out of Xeron North. So everything going out of Xeron North is everything going out of Xeron North to Xerox plus Hughes plus Rockwright. So I should say sum of everything going out of Xeron North to Xerox plus Hughes plus Rockwright. Right? It's a sum. So this is everything coming in and everything going out. Similarly, everything coming in to Xeron South from both Arnold and Supershelf, and everything going out of Xeron South to Xerox, Hughes and Rockwright. Right? Those are the constraints. Everything coming in should be equal to everything going out. That's it. So these are my constraints. So my supply constraints, demand constraints, and transshipment constraints. Now that I have all of this set up, I can solve this using the solver. So I'm going to go data and solver. Right. So again, objective function is here. This is where my objective function is. This is the sum of the two sum product functions. I have that. Again, I'm going to minimize the cost of transshipment. It's not maximizing, obviously. And of course, I'm going to change the GRG nonlinear. I'm going to change that to simplex LP. That change is made. Now we're going to look at the changing variable cells. So these are all my changing variable cells. So this is where you have to be careful. Changing variable cells, you have to say all of these cells here, comma, don't forget the comma, all of these cells here. Right. I'm going to try this again. I mean, the reason I'm having trouble is because this is a Mac. If you have a Windows computer, you shouldn't have trouble doing this. Just put a comma here and then it is. So B11 to C12, comma, B15 to D16. So these are all my decision variables. I'm going to add constraints just like last time. So supply constraints are going to be less than or equal to everything that is supplied has to be less than or equal to the capacities at those locations. So supply constraint will be G3 to G4 less than or equal to H3 to H4 for me. I'm going to click on add. Then demand constraint, so all the items that are supplied to the 3 demand locations should be equal to the demands at the demand location. So 50, 60 and 40. So Xerox should require 50 shelves, Hughes requires 60 shelves, and Rockrite requires 40 shelves. Add that. And finally the transshipment constraints. So everything coming in to the location 0 north and 0 on south should be equal to everything going out of the locations 0 north and 0 on south. So G13 equal to H13, then G14 equal to H14. Then I'm going to click OK. That's it. So A19 is where my objective is, B11 to C12, comma, B15 to D60. These are all my decision variables. Then I have G13, G14 is less than H13, H14. That's the transshipment constraints, everything coming in equal to everything going out. Then you have the supply constraint, G3, G4 less than H3, H4. And of course the demand constraint, G8, I8 less than or equal to G9 to I9. Corresponding values. Corresponding value should be equal. Once you have done that, we can click on solve. And there you go. All right. Now, according to this, the cheapest possible way to do all of this is cost you $1,150. You cannot do this for less than $1,150 according to this solution. Now, according to this solution, Arnold exclusively supplies to 0 on north and Supershelf exclusively supplies to 0 on south. And 0 on north will supply 50 units to Xerox, 25 units to Hughes and nothing to Rockrite. And 0 on south will send nothing to Xerox, 35 units to Hughes and 40 units to Rockrite. And the cost of all of this is $1,150. Right? Now, apart from this, this is something that I should have touched upon in the transportation problem. I will talk about that here. But a couple of things that I want you to notice is that these here are the actual values that are supplied out of Arnold. So 75 units are supplied and the capacity is 75. So the total capacity is used up. There is no excess capacity. The same for Supershelf. And the same goes for Xerox, Hughes and Rockrite. Demand is 50, 60 and 40 and all the demand is satisfied. And this is exactly what we expected. 75 units and 75 units. So capacity of 150 and demand of 150. So we knew that all the supply would get used up and all the demand would get satisfied, right? Now, in the transportation problem that we did before, I'm going to go back to that. In the transportation problem that we did, the total demand was 80 while the total supply was 100, which means that not all the supply was going to get used up. And you will notice that here. So in the demand constraint, all the amounts supplied to Northwood, Westwood and Eastwood match the corresponding demand because that's how much the demand is and all the demand gets satisfied. But with the supply constraint, the 50 units are supplied out of plant 1, which has a capacity of 50 units. So all the capacity is used up. But plant 2, capacity is 50, but the number of units supplied by plant 2 is only 30. 20 units go to Northwood, 10 units go to Eastwood. So plant 1 supplies 50 units, 5 to Northwood, 45 to Westwood. And plant 2 supplies only 30 units, 20 to Northwood and 10 to Eastwood. Which means that it has an excess capacity of 20 units. And we knew that that was going to be there, that there was going to be some excess capacity. The question is where the excess capacity was going to be. And it turns out all the excess capacity is at plant 2. Right? So you supply 30 units while the capacity is 50 units. So you have 20 units of excess capacity. So that is something that you can get out of the constraints to see if the capacity is used up for supply constraint and if all the demand is satisfied for the demand constraints. Now, if you wrote the transshipment constraints correctly, everything coming in should always equal everything going out. These numbers have to be equal all the time. It's only here where you could see some differences based on if you have excess supply or maybe sometimes you might have excess demand, right? And that's the transshipment problem. Like I said, it's a extension of the transportation problem, and it tells us the story when you have middle locations. Now, starting next week and the week after that, we are going to be talking about more and more complex network models. They all build upon the basic network models that we talked about today. So we talked about the transportation problem, we talked about the transshipment problem, how you set them up in Excel. So again, this setup is very important because we're going to use similar setups when we talk about the capacitated plant location problem, the capacitated plant location and the warehouse location problems, and all the other problems that follow through with that. So all the more complex network models that we do, they're all based upon the simple transportation and the transshipment problems, and we can do that's what we are talking about today. So there is a case problem that I put up, that's a transshipment model. So you're going to have to come up with the model, set it up in Excel like this and solve it and answer the questions that are asked there. It is obviously more complicated than this, but I want to see how you obviously be able to handle it. A couple of pointers. Now in this model, in this transshipment model, Arnold and Supershelf, it ended up that Arnold only sent items to 0 on north and nothing to 0 on south, but we did not restrict that. But restrictions are always possible. It is possible right at the beginning that we could have said that Arnold will only sell to 0 on north. Then you wouldn't have had this value at all. Or Supershelf will only sell to 0 on south. So when you have those special cases, you have to be careful how you deal with them, right? Say for example, if let's take an example here. So let's say that if 0 on north cannot supply to Rockrite. So if 0 on north cannot supply to Rockrite, the way you would see it in the problem is you would see there'd be nothing there. It's 0, there'd be nothing there. 0 on north cannot supply to Rockrite. If that's the case, if 0 on north can never supply to Rockrite, then your constraints are going to change. How are the constraints changing? So if you look at all the supply that comes into, say, Rockrite, right? So all the supply that comes into Rockrite, well, 0 north cannot supply to Rockrite. So when you write the constraint for supply, you only write the constraint. We'll just say that D16, instead of saying sum of D15 and D16, just say D16 is equal to 40. That's it. So constraint will change here. So this becomes just D16 because 0 north cannot supply to Rockrite, right? So depending upon how these constraints change, you have to make sure that you change the model. If not, you might end up with the wrong answers. Keep that in mind. So this was 8. I'm just going to leave that. That's it. That's the transshipment model. And if you have any questions, obviously you can ask me. And if you have any questions about the case problem, also you can ask me, and I will do that. So when I do the synchronous session this week, I will take another example of a transshipment model and go through that. I'm not going through a transportation model again because that is easier than the transshipment model, and so once you know how to work the transshipment model, you know how to work with the transportation model. So I will do another transshipment model when I do the synchronous session. For the time being, this is the video discussing the transshipment model, and take care.